Okay, so it's very important to pay attention to this lecture in particular, not because all the other are not that important, but because Raoult's law is a very powerful concept to understand in this specific section. Okay, so this guy is called Raoult, and he was a chemist, and he saw a lot of interesting things when working with solutions. So he first worked with nonpolar substances, which, remember, this is an ideal solution case. Of course, back then the concept was relatively new, so this was not intentional. And remember that they also work at low pressures, which favors ideal gases. Now, what Raoult saw was a very interesting concept, which we already deduced back here, but imagine getting to this observation experimentally without previous data or without previous concept of fugacity. There is no concept of ideality, just watching how these vapor pressure of components work out. He saw that the total pressure of the system was related to the partial pressure of A and B. So try to imagine that. He saw that the total pressure depended on a certain extent to the partial pressure of A and B. It was a proportion, so imagine that, a proportion related to the molar fraction. So he didn't saw a volumetric approach, maybe he didn't saw a mass approach, he saw the molar fraction per se. The vapor pressure of the mixture was never, so this is important, never, lower than the lowest vapor pressure component, which is of course this one right here, and never higher than the highest vapor pressure component. So I know it might sound obvious, but trying to prove this, especially in the age or times of Raoult, was a very huge concept. So this meant that even though you change the molar compositions of A and B, you will never be able to get higher or lower than the lowest and higher values. Recall that in equilibrium, right now we know that the fugacity must be equal, but before there was no concept of fugacity. So Raoult stated that the partial pressure of the vapor of each component of an ideal mixture of liquids must be equal to the vapor pressure of the pure component multiplied by its molar fraction in the mixture. Now, the pure component part is very interesting because it assumes that if you know the pure component vapor pressures of A and you knew the vapor pressures of pure component B, if you mix them, you could predict them, which of course right now makes kind of sense, but if you mix them at different pressures and conditions, not always will be the case. So for this, this law is very interesting for that because it started a movement, or let's say a theory, in which the prediction of pure states will eventually help to predict, let's say, mixtures, which is of course great. What we want to do is to be able to predict, without doing experiments, how A and B relate to each other. And essentially what we get in final conclusion is this. For an ideal gas, we will assume that the partial pressure of the component will be equal for the saturation pressure times the molar pressure, times the molar composition of that component, which is essentially this. We know is now simplified to this. Once again, we didn't have any coefficients back then, no activity coefficient, no fugacities. This was the first, or one of the first laws that Raoult proposed. Now it's interesting, for a binary system in which we only have A and B, we get this. Of course, this is true. Each one independently will be true. And if this is true, the molar composition must be also equal to 1 in both cases. And if we substitute, let it be, okay, let it be letter B, then xb equals 1 minus xa, and the same is true for y, and we input this data here, we will get this equation. I know it might be a little bit more complex, What I want to show you is that now we have only YA, XA, and vapor pressure of A and B, and total pressure. I know it seems a lot, but please note that partial pressure depends only on temperature. So if we change temperature, we will change partial pressure, but at a known rate. We have now only A and B. And it's great because we can now relate composition of A versus composition in the vapor phase of A. If we fix pressure, which we typically do, pressure will be always 1 atmosphere, or typically 1 atmosphere. We have now pressures, XA, fixed. We can now get vapor composition of A and temperature. If we further manipulate this is just the case mathematically, but we want to further exploit this. So the total pressure was equal, according to Dalton's law, to the addition of all the partial pressure of the gases. Replacing for the partial pressures, we get this data. This, of course, is mathematically a composition of this. And if we keep going, remember that this is true. If this is true, we send this P down right here, and we get this equation, which I don't know you guys, but seems a lot to me like a straight line. But there is no intersect, so we get kinda of a slope right here. You see the slope. And if we propose several data, if we know the total pressure, and we propose several x values, and we will start seeing that we can form, if we know the equilibrium, we form a line, which is not always, actually should not be always, XA equals YA. Essentially, this is Raoult's law. Of course, I know this is very theoretical and a lot of equations, manipulations. We will further understand this in the following exercise.